So we like to use the multi-physics simulations very heavily. In that light, we also are putting a lot of our designs on open source, and here's our open source address. For instance, you'll find there's a new simulation software out there that developed by the Army Research Lab. That's called ParaPower. It's free, and it's for very fast designing of the electrophysical system. And then from that, you'd want to submit it to a COMSOL or ANSYS. They'll give you more detail. The other parts you'll find are some of our designs. For instance, what you'll see is there's these are the DBC ones. We want to put the organic substrates on also. But if you're interested in a 25 kV DBC package, if you go to this onto this file, you'll have everything you need. It gives you the total SolidWorks. We talk about what the vendors are, where we bought the materials. This one's completely laid out. Feel free to use this. You could send it off to, we used Remtech, send them off. They'll make substrates for you. You can bring them in-house, you have the capabilities, or send them to us, and we can mount die, wire bond die, and encapsulate for you. We give you whose encapsulation materials we use. This has all been qualified for us to make sure we're getting like minimum leakage. A lot of what we're doing, for instance, in 3.3 kV die or package, is to look at how vendors can then go ahead, or developers, die developers can go ahead and do fast turnaround of packages. And so these are all online. We'll be adding more to it. This is the open source, what we're doing. Also like to acknowledge our team. Again, the Army Research Lab has funded a tremendous amount of this. Power America is able to provide us new equipment. And then there's a company, Reshow, has actually been working and providing us materials for us to be able to do the organic substrate materials, along with United Silicon Carbide, to be able to provide us die, you'll see, for some of our high voltage work. If you're not familiar with what we do in our lab, on the left-hand side is the pristine lab that doesn't look anything like this, because we've not been there for about 3 months, and also when we left, the students left a lot behind. But anyways, it looks really good right now. That's our full lab, but we have a new capability that we just added the end of last year, and we commissioned it, but we haven't got in to be able to actually fabricate and make circuits out of it yet. What it is this equipment, and again, this is going to be put online, so if you wanted to duplicate this entire lab, you can duplicate my entire lab if you want. I'll send you all the information about all the other stuff we have. But this is for the organic processing equipment. Again, it's like making printed circuit boards, but we're using these, instead of using polyimides, which are hygroscopic and which are printed circuit boards, we're using epoxies, which give us doesn't quite have as low a modulus as polyimide, but it has a very, very low modulus compared to ceramics. So when people talk about CTE, a lot of EEs talk only about CTE, coefficient of thermal expansion. What you really should be talking about is the expansion coefficient along with the modulus, because rubber's got a horrible expansion coefficient, but it's so soft, it never translates stress. So you want to look at soft materials to be able to say, hey, I can go long times and high reliability without having to translate stress into my die or into my solder joints, etc. So this is the equipment we use. We see up at the top, it's a mechanical router. You notice it has fairly good resolutions. These are phenomenal. We're talking about new wide bandgap devices that are down. They're getting smaller and smaller, or they're available at much higher power densities at much smaller sizes. Dr. Huang showed this could be a 16x reduction for same power loss on die. So now you have smaller heat points of heat generation. However, if you get the larger die, you get the much more higher levels of current capacity, or we can also look at higher voltages. So if we look at size, you can see that the plotter on the top can actually fabricate, and there's some things, the pictures to the left that shows how it can scribe out different patterns, and we'll see copper on organic, what it means. Then you can laminate. Notice that the size is a 9 by 12 inch size of board that you can process. If you're doing ceramics come in 5 by 7 panels. So 5 by 7, you have to fit optimally fit your substrate into that size. If you have a large substrate, you might only get one per panel. The panel costs, of course, ceramic are much higher than what organic materials are. So here we can have more substrates per panel, and that drops the price down. The same thing with, use the same thing for going from 300 millimeter to 400 millimeter wafers. The idea is to increase the size to get more out of the same in the same area. So if we look at also the other part is the final one at the bottom, you can do etching, use the left-hand side to be able to make your masks. You can do etching, we can do plating, etc. We have 5 bays there. And so this gives us the capability to do full research in organic substrates where we can do multi-layering. And eventually we want to get into embedded components. So we want not only multi-layer power, but we also want to do embedded components. We also have a new capability in the lab, which now is a small wire bonder. We've used HESA, has been providing us with the heavy wire bonder for years. This gives us down to 4 mil wire capability, but now with the TPT system, we can go down to the 2 to 1. Actually, it goes from 4 down to sub 1 mil wire. And we need this now because on the smaller DVC, on the smaller wide bandgap devices, the gate regions are becoming smaller. So, it's very typical in many of the big modules with IGBTs, et cetera. You might use one size wire for your power module, for the power die, but you use smaller wire for your gate structures. This gives us the capability to start mixing the different wire sizes down smaller. I want to give you 2 areas we're doing research in not reported here. And this is the high voltage thrust we have. And then Sushwan will be talking about the low voltage thrust. Excuse me. So in the high voltage, through Power America, we have a project where we're developing substrates for die development. We're not interested in the packages being something that you go off and once a die is packaged, you go and do reliability work on it because then you're testing the reliability of the packaging. And in my lab, I try to stress that we don't do reliability packaging. We don't do, I hate to say it, reliable packaging, but the idea is to drive home using manufacturing compatible processes. This is how you might do it. This is how you would do it. And of course, we have strong modeling behind us to be able to do this. For instance, we might use a soft solder, but we can go ahead and simulate with sintered silver. And we would have sintered silver, except of course the virus kept us out of the lab. So if you're using if you use sintered silver, we know what the process is, we know what the characteristics are, we can model all that and say, okay, this is the performance we see using soft solder that we produce. But again, we're looking more at the electrical and thermal performances and not necessarily the mechanical performances long term. So, but we do want to make sure that we're compatible, and we want to show the comparisons between, for instance, using ceramics, getting into your organics, going from polyimides down into epoxies, et cetera, and showing the mechanical aspects of it also. But we try not to build packages that will be, it's really the purview of the true manufacturers that do high volume manufacturing that can produce that can embed the reliability into the actual packages for final reliability testing. There are institutions like the University of Maryland does tremendous amount focused directly on it. Our colleague Patrick McCluskey does tremendous amount of reliability testing and development. So you'd want to do, so they're the ones that do the reliability research. The other part we're doing is we've come up with, before in the past, we've done 6.5 kV DVC using the super cascode structures, 6.5 kV 200 amp module with DVC. But the problem is, of course, you have a lot of capacitive couplings between high voltage devices. So what we're doing now is we're actually focusing on saying, okay, well, let's get rid of, in fact, Dr. Bhattacharya and I had discussions a couple of years ago saying we really need to get rid of the metal substrate. We can't do capacitive coupling into a common substrate. And so that combined with the organic material that we're using now, we're able to build substrates that and mount moldable die. And the nice thing about the cascodes is that you're able to distribute your power losses across your die. So you have a choice. You want a high power module, high current, high voltage. You can either put high voltage, low current die, a horrendous amount in parallel, or you can take a high current, low voltage die, such as the JFETs, and put a horrendous amount in series. And we've chosen the series approach because we can get much better higher power thermal management, et cetera, from the lower voltage, much higher current die at much higher speeds. You know, we're reporting 45 nanosecond switching on our 6.5 kV 200 amp module, DVC. And we should be able to go faster on this because of the organics. We're not capacitive coupling. And so what we're going to do is we have a 6.5 kV module that we've developed and we're going to be building. And then we're also going to take those and 4 of those and couple those together to be able to get into the 24 kV 100 amp space. And these are the projected metrics through our heavy multi-physics simulations that we use. Why are we here? What's the trend in power electronics is to higher performance with smaller wide bandgap devices. And you say, well, the devices are getting bigger because we look at 1 millimeter. My rule of thumb is all power die will eventually be 1 centimeter on a side. And that's kind of how I look at where the future always goes. But what we have find is that in the smaller sizes, we do find much more electrophysical integration, which is really key for us from a packaging technology. And again, I'm electrical, so Schwenn's mechanical, so careful who you ask questions of if you want a really good answer. So what it is that power electronics is hardly packaging, it's hardly adapted any power from, any packaging technologies from that we developed ourselves. We've always adapted it from microelectronics, and we're doing the same thing now. As the die gets smaller, we see more and more microelectronics packaging technology being brought into the power packaging world, such as organics. And so this is in keeping with what we're planning on in our research going forward. And what we're focusing on, again, I mentioned that there are other organics we're typically using in printed circuit boards, et cetera, the polyimides, et cetera. But instead, we're focusing very heavily on these epoxy rosin composites. And what the composite is that these companies are taking epoxy rosins and infusing them with aluminum nitride and aluminum oxide, alumina powder. And so therefore, they're getting the thermal conductivities up while still maintaining the benefits of epoxies. So what we're going to look at here in this talk is going to be applications of 1500 volts and lower, and specifically introducing the new BidFET developed by Dr. Balaga and his group, which is a bidirectional field effect transistor with phenomenal capabilities. So as a review of where modules have been, if you want to do topside, then you do topside interconnects. Topside interconnects, if you think of the power overlay that was developed by GE, you know, they're using basically polyimides on the top, polymers on the top to be able to do interconnects. Semicron did something very similar where you're taking a flex circuit, if you want to think of it, a flex circuit, and being able to interconnect all your power die on top. And then you also have Mitsubishi that did direct lead bonding, and that's where you're putting heavy metal on both sides of your semiconductors, but the top side is for your interconnect and the bottom side is where you're drawing your heat from. For double-sided power modules, and again, if you want to ask questions, please note the page numbers and scribble it down, and we'll have all those covered at the end. International Rectifier came out a long time ago. They took their die, they used a thermal epoxy into the lid. You flip the lid over, solder it down, and then you're able to draw heat off the top. Note that the lid would be electrically hot, so therefore you have a dielectric sitting at your dielectric insulation is done with the fluid of air on the heatsink at the top. And the rest of it then would be flipped over so you have drained to source. What Taiyo Denso did is they did DBC sandwiches, and then these sandwiches then all fit together on the left-hand side. You can see how they would squeeze them all together, have some nice thermals, water cooling, fluid cooling between each of those, sandwich them all together. But here the dielectric isolation for the die is done with basically a DBC, so the ceramic at the die is providing the insulation, the electrical isolation. If you look at what Liang did at Oak Ridge, he took in his package, he did DBC sandwiches. So again, the insulation is with the ceramic, and then you'd bring out your heat through all the ceramic and into the cold plate. If you go back 2 years, 3 years, this is the dissertation work done by Young Shu. Young's now at Tesla. Young Shu, and the challenge was, how do you get the maximum heat out of the chip? And what he said, well, first of all, we'll take the dielectric insulation layer and move it to the second level of packaging. So instead of having it first level under the die, we're going to move it to the second level, basically board level, and cool it at that point and give you electrical isolation. So this, what he showed here, takes the heat sink at the top would be electrically hot, sitting on, let's say, the source gate side. The bottom heat sink sits on the drain side. It's coupled together directly in contact with the die with a mechanical buffer. He used a Moly tab to be able to do the one side of stress management. And then also in the center of it for the gate drive, he then implanted a flex circuit to be able to pick up the gate interconnects. And what he showed was that you can have the same, if not a little bit higher power density using direct connect with air isolation than you can if you do it with liquid cooled DBC structures. Now, of course, you want to get it, you need to be able to say these are running hot, but for most cases, we're in full control at the second level of how we build housings to be able to have our shrouds to be able to provide airflow, et cetera, through all of this. So you can look at his dissertation, he goes through all of this. Now, I know I'm kind of rushing quickly because I want to get to Shixuan. He's the star for this show. But I want to give a little background on these epoxy rosins that we've been looking at. If you think of what you do traditionally is with the DBCs, you have a heavy base plate, you solder down your DBCs, which have your die on top. But instead, what Mitsubishi did 2 years back in 2016, here's the references, they actually decided to go with, and that's what we're doing, is going with this, the epoxy rosin. They say a rosin, but it's an epoxy rosin. As the electric isolation layer, like you would for BBC, which is copper bonded on ceramic, but the layer purple, instead of being ceramic, is going to be some kind of an insulating layer. In their case, the rosin, organic epoxy. And so what they show then is they find that, for instance, the CTE is much closer to copper, so that you're measuring copper's organic copper. Next, you get a 35% increase in thermal performance. And we'll talk about this in the next slide, because the key to the organics is dropping the thickness down. Okay. And yes, you're going to have higher capacitances, and then you got to deal with that problem. And that's how we've done it differently, by you looking at pushing isolation to the next level. But anyway, so you have this isolation, so you have 35% better reduction in your thermal impedance, fewer interconnection layers for low profiles, because you're dropping the DBC down to very thin copper and then very thin ceramic. And keep in mind, the copper on top on a sandwich is for the interconnection for electrical purposes. And typically, this would be due to current carrying capacity. And you'd want the copper thin to be able to, so what happens is if I have no copper, then if you want to think of it, I have no copper, I have great thermal conduction, but I have very, very poor current spreading. If I keep increasing the copper, then I start saying, okay, I get more current two-dimensional spreading of current. But if I made the copper, let's say, 3 inches tall, well, I'm not spreading anymore. I mean, I've done all the spreading I can do in the first actually 2-3 millimeters, and the rest is strictly thermal resistance. So there's an actual optimum for copper, and it depends on what your thermal conductivity or isolation layer is, if you're doing a sandwich, of how thick copper you want for your current distribution and for your thermal spreading. And if you go above that, you only add thermal resistance. So it's not like thicker the better. You want to kind of get away from that paradigm. And anyways, and also the thicker your copper, the higher it is on your stresses within the system. So you want thin copper where possible. The top side is for electrical interconnect. The insulator in the center is for dielectric isolation. And then the bottom one is to do stress management. So there's 3 different functions, 3 different layers, and they all are unique, and you want to be able to optimize across all 3 layers when you start looking at building these modules and building circuits on these modules. Better thermal cycling reliability, less cracks because the organic is much more forgiving. It's got a much lower modulus, and it depends heavily on the rosin interface materials. So here are the rosins materials that we looked at, or that we have been supported with. Risho's been doing this with working with us to introduce us to these new materials they've done. And why is it coming up now? Well, because the microelectronics world has actually been getting into this in a different way, and I'll show you in a second. So on the left-hand side, you have glass reinforced. This is your typical printed circuit board material. This is what we do all our gate drive circuits on, and so. But on the right-hand side is when you start getting into these epoxies that have these dopants in them. I'm sorry, not dope, these infused particles into them. And you can, in this case, from Risho, if you want, or we're going to do it ourselves, you can have copper foil sitting on an isolation layer, which is the rosin, and then you're going to put that onto a heavy copper or heavy aluminum plate. Well, this is insulated metal substrates. This is something Bergquist used to do and then other people used to do and still do. So this is your IMS approach, and this is what microelectronics has now rediscovered is IMS systems, insulated metal substrate systems. Before, in the previous slides, Mitsubishi did insulated metal base plate, IMBs. This is the traditional IMS. IMS has been around for many years. And so it's copper foil you can get of different thicknesses on up to like 20 mil thick. Insulation layers we'll show in a second what the layers are. And then the thick base plate or copper plate in the bottom. Tell me what cost you want, what thermal performance you want. You can also go ahead and so this is a whole material system we look at. Here's just the bonding layer, the B stage material. This is partially cured epoxy. You can use it to bond together many layers. You know, think of it as just an epoxy glue, but it comes in a nice sheet form, uniform thicknesses, also has very high voltage withstand capability and high thermal performance. So we can use these to be able to stack. And then what would we stack? Well, the last one would be your typical copper on polymer, copper on polyimide, copper on organic epoxy. It's copper foil bonded to your B stage material, which is your insulating layer. And then you can then pattern this and stack these up. You can pattern this and you could stack it onto the IMS and stack up so you can get multi-layering. You can use this for embedding. You can put in the bonding layers, the center one as fillers between if you need, or it can actually squish down depending how hard you want to press it. So this is a system now that allows us to do, again, multi-layered substrates with moving towards embedded components. What we're interested in Power is their top line performance, which is they have materials now at up to 10 watts per meter degree K. We did a lot of the research. If you look at our publications, they're done with 8 watts per meter degree K. And so now we're looking at, and with 8 watts per meter degree K at 120 microns, we perform thermally better than alumina DBC. So if you were to do, let's say, 8 mils of copper, 25 mils of alumina, and 8 mils of copper, the alumina of 25 mils, 625 microns, 25 mils, performs a little less well as this 8 watts per meter degree K, 120 micron organic material. So we can beat alumina. When it comes to aluminum nitride, we can't compete. So if you walk in the lab and say, hey, Doug, here's what should I do? And well, if this is really high performance, you need aluminum nitride. It's going to be a metal clad ceramic, and of course, aluminum nitride or silicon nitride, it's going to be metal clad ceramic. Now, if you're saying, I need something lower cost, I need something and that's the big key is lower cost, something lower cost, and I want to have it lighter, what do we have? Well, here's the organic approach. If you could done it with aluminum oxide, alumina, DBC, this would be a better approach, particularly because the organics give you much higher reliability because the modulus is so low. And keep in mind, this is the thermal equation. It's the thermal conductivity times the length, and that's the length of the path that the heat goes through. which is only about 120 microns, NOx 625 microns, and of course the area. So as you get larger die area, you can get lower thermal resistance. And it's really about thermal resistance, not thermal conductivity. And it's all about CTE and modulus. It's not just CTE. You also can have other parts, other performers in this path. And then, of course, the bottom ones are the ones that are typical printed circuit board. So if you want to have a gate drive circuit that you need some fairly good thermal performance with, but nothing, you're tired with just a simple 0.5 to 1 watt per meter degree K printed circuit board, then you can start looking at the epoxy boards with little higher thermal conductivity. So bottom side, gate drives, top side, power. This is the 8 mil. I won't spend too much time. I want to move on to Shushen. But if you the points here is if you look at the graphs that we're showing, the breakdown voltage, the left side with the blue line shows that here for 120, this is 120 micron thick sheet across 3,000 hours. You can see that it's very, they use partial discharge tests when they do these. You can see it's very stable with the voltage capabilities, 5 kV at 120 microns, something like, I think it's like 44 kV per millimeter. We're up in that range. I think that's what it is. And then, of course, how does the actual material degrade over time? Well, the peel strength is one of those. That's the mechanical part. And this is all done at 175 degrees C. This material is qualified to go up to, if you see, you can go up to, where's the 270 is the TG. But again, that's when it starts to soften. But we have testing, they have testing on up to 300 degrees C, stable to 300 degrees C. So this material gets us well above 250 degrees C operation. And we're using this for high temperature, where we're doing our 300 degrees C research. And it also gets you high voltages at the same time. This is some testing we did on leakage currents, and I won't bother going through this, but this has been published in the past. But again, we have really good low leakage current for high voltages. This is the 10 watts per meter degree K, and again, the same graph showing that for voltage withstand, it kind of drops down as we go over to more time. This graph may be updated because I know that this was under development when we were doing these. So I want to say that this may actually be a better performer than what's shown right now. But again, the material does not degrade over time due to peel strength, which is critical. And this was all done on a DVC plate, a DVC structure. This is the cost performance. You can see that aluminum nitride, this is how much space you get per dollar. So instead of dollars per meter squared, we did meter squared per dollar. But if you want to look at what the cost of the materials are, you can see that they're substantially lower in cost. Right here on the right-hand side, this is the dollars per meter squared, and alumina is pretty cheap. Aluminum nitride ups the cost substantially, and the epoxy rosins for substrates is very low. Again, it'll be a much lower profile, lower cost as far as material goes. Again, you're dealing with larger sheets, so you have lower manufacturing costs. So it's a lower cost, better performance, but you can't compete with aluminum nitride. This is one of the projects we did first out of the gate by Shushen, by Xin Zhao. And Xin had actually built this up, did some testing, and did a double-sided power supply. The last thing, so then at this point then, I'm going to pass this over to, I hope, I pass this over to my presenter, my co-presenter, Shushen. Are you, there you go.
Yeah, hello everyone. I'm Zixuan. So I'm a PhD student in EC department at NC State, but my background is about mechanical engineering. So later I will focus more on the thermal, mechanical, and manufacturing. And now I'm going to introduce one of my work, which is a double-sided cooled silicon carbide half-bridge power module using our organic substrate. Okay, so it looks like I cannot control the screens.
I think I need to pass to you the, I need to pass to you how to the control, I believe. And I don't know how to do that.
But okay.
Go ahead, John.
You should be able to take control, Suzanne. It looks like you've been past it. See if you click on the slide, and if it click a second time, see if it advances it.
There you go.
There, okay, yeah.
Oh, okay, I see.
You found the back button too. That's good.
So, okay, I'm not sure whether I'm controlling, but anyway, okay. So in this slide, I'm going to introduce the power device package in this double-sided cool power module. So it is a silicon carbide bidirectional FET. We called it BitFET, which is proposed by Dr. Bodyguard at NC State. So it is a monolithic device consisting of two JBS FET, as you can see in the green box here. And each JBS FET comprises one JBS diode and one power MOSFET in a unit cell. And in the right figure, it is a real sample. So there are only 4 terminals, G1, T1, G2, T2. And because it is a dual gate design, so there are 2 gate paths for each JBS FET. So basically, bidirectional power switches can be used in matrix converters or cyclo converters, and with the multi-stage inverter topology, can facilitate high switching frequency in AC-AC conversion. So this enables us to reduce the power conversion with intermediate energy storage components, so resulting in higher power density and better efficiency. So in the bottom figures, there are several prior implementations of bidirectional switches. So they basically employed various combinations of discrete power transistors and diodes. However, in our BitFET, our device is a monolithic device, so we can save more area to achieve higher power density. So go to the next slide. Yeah, so here's about the packaging. So here's the double-sided cool half-bridge power module and providing Kelvin source connection for the driving loop. So as you can see at the bottom, there's a KS stands for Kelvin source. So basically we apply 2 10-watt per meter degree K ERCD substrates for top and bottom substrates. And yeah, as you can see at the right figures. And next, in order to reduce the crosstalk between the power loop and driving loop, so there are 3 power terminals and 8 signal terminals are separated at 2 opposite sides. And this power module consists of 2 1x1 centimeter BitFETs because it is a half-bridge topology. And finally, we apply spacer components on the top surface of the devices. As you can see at the bottom right figure, there's a spacer, like a sandwich structure in the middle. And the function is to reduce thermal and electrical parasitics. So it is very straightforward, easy to understand. On the other hand, it can also adjust the mode flow quality of the encapsulation process. So adding the spacer, we can increase the Z height. So the mode flow will be easier to fill every gap in the power module. And on the other hand, it is critical to think about the insulation distance because without the spacer, the entire module can be very thin. So we need to have the spacer to increase sufficient insulation distance. So because after we will usually will mount two heat sinks on the top and bottom. So we need to be aware of the insulation distance between the terminals and the heat sinks. So the next slide. Okay, so this part is about the thermal modeling. Because of the symmetrical structure, so I only consider half of the power module in all the following finite element modeling. So I assume perfect cooling on the top and bottom cases because I ignore the convective thermal resistance, only consider conduction heat transfer. And the boundary conditions is about I apply the heat source on the top surface of the die. To quantify the thermal performance, it is common to extract the thermal resistance junction to case, RJC, and it can be defined as the temperature difference between junction and case divided by the power passed through it. And you can see the right table, it is about the dimension of our power module. And click on that, it is the schematic of the cross-section. So because it is a double-sided cooling structure, so we will analyze both top and bottom thermal paths. And here the red dashed line shows the heat flow to the top and bottom. Okay, so go to the, yeah, let me see if I can use the laser pointer. Okay. Okay, so this slide shows the thermal resistance breakdown, which helps us to identify the key parameters or components. So first, let's focus on the top thermal path. Look at the bottom figure. It shows the heat flow to the top. So in the simulation, I only applied the heat transfer coefficient on the top surface, top case here. So because I need all the heat to go upward, and then I will capture the temperature difference between junction to top case. Then I can calculate the thermal resistance, RJC top. And in addition, we can use the same concept to extract each layer thermal resistance. So here's a breakdown. Yep. Okay, so as you can see in this chart, ERCD layer contributes the major thermal resistance because of the relative low thermal conductivity compared with solder and copper spacer material. Okay, so the right side is about the bottom thermal path. So in the right, so for the RJC bottom, it is clearly lower than the top, RJC top. It is because the area of the spacer is only 60% of the device. So less area will lead to the higher thermal resistance. So that's why the bottom RJC is lower than the top one. And by paralleling top and bottom RJC, we can get the total, or we call the equivalent RJC here. So it's around 0.086 degree per watt. And besides to the RJC total, we can further calculate the maximum power that the power module can dissipate. So it is around 1.7 kilowatt per bit fed. And you can notice that this value is extremely high because I assume a perfect cooling condition at both top and bottom cases. So which means this value is the upper bound or upper limit of the heat dissipation capability. So you cannot exceed this value. Okay, so in addition to the thermal modeling, I also did the thermomechanical modeling for characterizing the reliability in the thermal cycling test. So here are the conditions based on the JEDEC standard. on the right side, it shows how CT's mismatch induce the thermal stress. For example, in the low temperature stage, copper spacer would shrink more than the epoxy molding compound, the black material here. Therefore, it can cause like a die crack or solder layer delamination. In the simulation, I applied the anode viscoplastic material model for considering both plastic and creep behaviors in the solder material. Next, so it's about the Fatigue-like prediction model. So in order to quantify the lifetime of the power module, I applied the Coffee-Manson formulation, so which is commonly used in the industry. So in the equation, NF means the fatigue life, and epsilon here means the equivalent plastic strength, and the C and eta are the constants that depend on solder material. Okay, finally, here are the criteria in the mechanical simulation that I defined. So basically, I monitor the stress and strain on the die and solder because those are common failure points. Okay, so here, so now I'm going to share our thought process of how we design a power module in terms of reliability aspect. So first of all, there are two key factors in design and modeling. They are material and geometry. So in this section, I will discuss the material selection first. As you can see in the table here, I parameterize Young's modulus and CTE of 3 dominant components in the power module. So including the spacer, dielectric, and the encapsulant material. The reason I chose these 3 components is based on my experience and the literature review. So there are 200 design points in my parametric study, and the ranges and parameters need to be the ranges of the parameters need to be reasonable, and it can depend on manufacturing capability, cost, application, and so on. Okay, so here's the bottom is the sensitivity chart. So the concept of the sensitivity analysis is to identify the parameters which dominate the objectives, like the stress or strain over at the bottom. So in the figure, so the length of each column indicates the importance of parameters, and the longer columns mean the higher influence. On the other hand, the polarity of columns, like above the horizontal line or under the line, so the polarity signifies the trend of the influence of parameters. So positive columns means the relation between parameters and objectives is in direct proportion, and the negative column, it means it is in inverse proportion. So let's see an example. So if we want to reduce the plastic strain here of the solder, so look at the blue column here, we should reduce it is a CT of spacer, so we should reduce the CT of spacer for lower plastic strain because it is a positive column here. So same concept. Look at the yellow column here. It is modulus of encapsulant. So it shows that we need to increase the modulus for getting lower plastic strain. So actually, this chart helps us to understand the whole picture, all the interaction in terms of the mechanical reliability. And at the right side, as I mentioned, there are 200 design points in my parametric study. So these points cannot pass the criteria in previous page will be screened out. So therefore, in this figure, each red point represents one design point that passed the criteria. And this figure takes a spacer material as an example. Some candidates for spacer are shown here, like MO stand for molybdenum. Maybe we called it moly. So it shows the moly, copper moly, and copper alloy here. So in their area, they cover some feasible solution, some red points in their area. So and basically for the spacer, we need them to be thermally and electrically conductive. So they are usually metal materials. Okay, so this graph can clearly identify viable solution. Okay, so these slides present some examples using moly or copper moly. Like here, moly spacer, copper moly buffer plate, moly buffer layer. Yep. So those study applied those spacer material adjacent to the semiconductor device, yeah, either above it or underneath. So these works also indicate that our analysis is on the right track. So it tells us why people choose moly or copper moly for reducing the mechanical stress. Okay, so in addition to the material selection, I'm going to discuss the geometrical dimension. So how do I determine the thickness of each layer? Also in the reliability perspective. So the spacer here, I chose copper because it is the cheapest solution and it is easier to access. Okay. Okay, so here also presents a sensitivity chart showing which parameters are more critical, and it indicates that like the strand here, so it shows that a shorter spacer can help us to reduce the plastic strain. So we need a smaller spacer here. Okay, so on the other hand, at the right side, I also carried out a multi-objective optimization, and the best design can be the set of solutions, which is depicted by the Pareto front here, the red line here. Okay, so each blue point represent one design point, and the points on the red line means those are all optimal solutions depending on your requirements. Okay, so what does that mean? It means that the designers need to select their own solutions by evaluating the trade-off between mechanical and thermal performance. So, for example, if I need the fatigue life higher than 1800 cycles, it's over here. So that means my optimal thermal resistance is around 0.084 degree per watt. Because our target is going toward to the top left side, higher fatigue life and lower thermal resistance. So our target's in this area. Okay, so on the other hand, if you need lower thermal resistance, that means it's going to the left direction. That means you need to sacrifice part of fatigue life because your lifetime is dropping when you go left. Okay, it is the idea of the Pareto front. Okay, so in summary, your best solution can depend on product application, your industry, and your operation environment. So therefore, the best solution can be varied by different designers. Okay, next slide. Okay, so due to COVID-19, all the prototyping is delayed, but still underway. So, so here I can briefly show our plan of the fabrication flow chart. So first, for this module, we will do the die bonding and the leaf frame bonding with higher melting point solder. And then next, so here's the example here, previous work. And then we go to the wire bonding for the gate pad. Because for the top source pad, we will use a spacer later. And then next, it is about the top substrate. So we will bond the leaf frame and copper spacer, also with high melting point solder. And next, we will assemble top and bottom substrate by lower melting point solder. And finally, we will do the encapsulation. Okay, so here's a final slide. So yeah, here shows the development plan for our organic packages. So here you can see from the left, it is about the plan for top-sided cool discrete power package. So all the process here can be done in our lab. So as the starting point, we will carry out lots of fundamental studies for characterizing its thermal, mechanical, electrical performance and comparing that with commercial discrete packages. So it is our benchmark because all the processes are standard. Yeah. So next, we focus on a patternable dielectric structure for integrating more devices in a single package. So such as we can integrate a gate driver or some passive devices. So you can see the second step. We not only do the patterning for the top conductor layer, copper layer, and also the dielectric layer here, the green layer here. Okay, so because we want, here's the structure we want to achieve. We can place the low power dissipation devices on the top upper layer for and the high power devices at the bottom layer. So we can let the high power device has a better lower thermal resistance. And also on the other hand, we can stack more layers, I mean dielectric layers and copper layers on the top for solving the routing problem. Yeah, and different from the DBC and different substrates, our laminate structure can provide smaller copper trace space and width, like 100 micrometer or even 50 micrometer for bonding flip chip devices, maybe in the future. So, so basically it can achieve high integration capability and high power density. And the last one here, other than dual substrate structure, I showed in previous slide, we can also achieve double-sided cooling by embedded structure here. So not only higher thermal performance, but also better switching performance by removing all the wires and decreasing the interconnection distance. So in addition to embedded multiple devices, it is also possible you can stack other packages on the top. So for increasing the integration capability. Yeah, because our top surface can be solderable. Okay, so so in conclusion, we are trying to bring in a high performance and cost-effective packaging solution by using our organic material. And on the other hand, we are also thinking about opening more possibilities, not only in package level, but also board level or even system level, because our target is to provide a complete solution, not limited to packaging. Okay. Yeah, that's all my presentation today. So any comments or questions?
Okay, thank you, Xian and Professor Hopkins. We do have a number of questions. As a reminder, we are actually at the official stop time for the webinar. However, we had some great information presented here. We have a good number of questions that we would like to address. So we're going to stay on and address all the questions that have been asked. As a reminder, this is being recorded so that PSMA members can request a copy of the recording. For those who want copies of the slides, if you're not a PSMA member, you can reach out to Professor Hopkins. His email address is at the bottom of every slide there, and you can get, and he'll be happy to send you a copy of the slides. First question we have, and this may have been addressed later in the presentation, but the question is to Dr. Hopkins, was thermal shock testing performed on the epoxy attached to check for delamination or peel?
No, we have not done thermal shock testing on these materials yet.
Okay. Next question we have, and the bulk of the rest of the questions are all aimed at Shujan, but
let me, I hate to interject. Let me mention this though. When I say we haven't done any testing, there's a whole nother area of our research which we're very, very involved with, which is solid state circuit breakers. And so there's a whole nother, in fact, there was just a master's thesis just done on that by Baji Ballard. And in there, we've been looking at a lot of thermal transient management. And in that, we've done things such as foams, thermally conductive foams. And so we have a large set of simulation. Again, we're very heavy into the multi-physics, so we can see how deep we go. And looking at high thermal transient, high power systems. We're looking at voltages and currents, in 10 kilo, we were looking at a kiloamp of current with a 10x trip. So that would be 1,000. There would be 1,000. It was 100 amps with 1,000 amp trip, and we also looked at 1,000 with 10,000 amp trip, and high voltage systems. So we've been looking at that very heavily, but we have not done the actual thermal testing, shock testing. Okay, sorry.
That's okay. No, thank you. Thanks for that clarification, and I think that should certainly address the question. Next question on slide 22. What is the spacer material you use? What considerations, technical, does one need to take for spacer material?
Now it's controlled by Dr. Hopkins. You move to 22.
There he is passing. There we go. This is 22. Great.
Yeah, so here the spacer material, we use the copper material because as I mentioned, based on my analysis, it shows that it is feasible. It can pass my mechanical criteria. So that's why I choose the copper. And also it is less costly and it is easier to manufacture or easy to access, easy to get it. So that's why we finally decide to use a copper spacer.
Okay. Next question on slide 23. So we can just go to the next slide. What is the spacer used here?
Yeah, so as you can see the table here, I use the copper spacer. So its function is not only to help to reduce the thermal resistance to create another thermal path. It also can carry the current. So it is also it is thermally and electrically conductive. Yeah. Two functions.
Okay.
Yeah.
All right, I'm going to skip the order of the questions a little bit here because we have another question on slide 23. So since we're on that slide, we will stay here, and that is the question is, what is the dielectric strength of this epoxy resin on page 23? So again, on this slide, the
okay. Yeah. So based on our material supplier, so it can withstand 5 kV at 120 micron. Yeah, so 5 kV at 120 micron.
Okay. Next question.
And we've been looking at we've been looking at potting materials specifically. So we actually have several different ones we looked at. And again, the supplier that supplies the ERCD can also supply. They also supply potting materials and are able to do testings, with partial discharge testing, etc.
Yep. Thanks.
Okay. Good. Thanks for that clarification as well. Next question we have is: you mentioned that you work with Unified FETs. What are the key benefits separating silicon SOC JFETs from other brand JFETs and MOSFETs? What makes them better?
Okay, so the JFET is a normally on device. It's and of course it's junction field effect, and so it's almost an apples to oranges comparison. No, you can't have normally off JFET, et cetera. But for us, for the supercast code, the idea is that if you're using a string of JFETs, you have a silicon MOSFET at the bottom, very low voltage, very high current, 25 volts or 35 volts, handling 100, 200 amps. And then you have the JFETs that are in series above that. And so now I can send you references to read through. They're pretty straightforward now. And the idea is that because they're normally on and you tie gate to source, when you lift the source, you're basically doing source switching. When you lift the source, it turns the gate off. Well, if you think of, let's say, a JFET with it having a MOSFET in the source, when you open the MOSFET at the source of the JFET, and the JFET gate's tied to the ground or source of the MOSFET, you open the source of the JFET. JFET sees a reverse bias across its, actually positive bias, but anyways, reverse bias across its junction, and then turns the device off. Well, if that was in series with another JFET, it would then lift the source of that JFET and negatively, you'd polarize in negative direction across the junction, which would turn that device off, and that device would turn the next device off. And so you have this self-initiated turn-off of all the series devices. But the JFET itself has advantages because it's junction. You don't have degradations necessarily in high temperatures of the oxides associated with the MOSFETs. So it has a lot of potential in that. It's also, since it's junction rather than field, you're able to switch them very, very fast. There's people out there that really would like to do JFETs, and my original solid state circuit breaker work was using JFETs because they're so much faster and they're so much more robust. But again, you've got to deal with a normally on device and different approach on how you're going to look at the device. But there's pros and cons. So when you compare JFET, we're talking about silicon carbide now. When you compare JFETs to MOSFETs, there's pros and cons. So I could say.
Okay. Thanks. Next question. Has anyone considered embedding the epoxy resin in the EMI drain? Excuse me, start again. Has anyone considered embedding in the epoxy resin an EMI drain shield on the cold side to return the conducted EMI back to the DC bus source? Another thin layer of insulation would be needed underneath that, but the EMI gains would be tremendous. Total system size, including EMI filtering, would go down, I believe.
Okay, so this is actually very interesting you're bringing this topic up because we have another PhD who's been developing he's actually looked at developing what he's labeled as electric field flow, and has been looking at, in fact, it goes beyond what you're describing. There's better topologies than that. And there's two aspects of it. One is specifically looking at how to do this management of field control because of the capacitive coupling typically. And you say EMI, you always want to make sure it doesn't leave the module. So that's why we're talking to you about embedded components where you can put your bypass capacitors right into the module, et cetera. And we're working with Kemet on some very advanced capacitors they have. But to this other point, we're actually dealing with this whole modeling aspect, particularly of electric field flow, which he's hoping can actually be put into, let's say, a Maxwell simulator and in this Parapower simulator, so that you can now have a handle on actually looking at how electric fields can be actually, as you change layer thicknesses, spacings, let me say differently. Layer thicknesses is one of dielectrics. Also, positioning of different dielectric materials within the structure to do field warping, to be able to optimize the voltage profiles on on the highly stressed dielectric areas. And for instance, one of the places is, you're going to use a silicone gel, then you have to be you want to make sure that your dielectric stress at high field intensity points is being managed so that you don't have localized breakdown and degradation over time of your encapsulates. And it's one of the, so we're actually we're just starting to publish. We now have a transactions paper we're actually in draft that I'm reviewing in that specific area. It's very interesting to be able to start looking at multi-permittivity materials at critical places within the structures to get electric field morphing. There you go.
Okay, great, thanks. And maybe a topic for a future roadmap presentation, Deval, if you can note that. Does the choice of spacer depend on whether the die is silicon or silicon carbide or GaN? If so, how?
Yeah, so I think I can answer this question. So basically in the mechanical reliability perspective, silicon carbide and gallium nitride may have different CTE or modulus. So yes, it can affect the result. Yeah, so it is not necessary to be copper spacer. It can be other material or with other thickness. So it is not necessary to fix at the copper material. Yeah, because the device can have different material property. So yielding different rigidity in the power module.
Okay, next question is on slide 26. Question on the chart there, so if we could advance a couple slides. There we go. The question is on the sensitivity chart. How did you create it?
Okay, so I use the software which is ANSYS. So in ANSYS Workbench, there is a built-in tool. So it is in the, I think it is in the design of experiment or optimization tool. So there is a function you can input your parameters and specify your objectives. Then it can auto-generate this chart for you. Yeah, so it is a built-in function in ANSYS. Yeah.
Okay, thank you. Next question we have is, does the manufacturer of the epoxy control variance well to guarantee a low partial discharge? If the oxide particles are not well distributed and size controlled, partial discharge in the epoxy will be higher in certain areas, increasing failure rate.
Yeah, so it is a good question. So because the data was provided by our manufacturer. So, but yes, we need to characterize by ourselves. We need to qualify it. So under different thickness, different temperature. So those experiment are underway. Yeah, we need to do that. Yeah, but we haven't done that. Yeah.
Okay.
Yeah, but let me also add though, and so we do our own verifications because we want to make sure in our lab that we actually can reproduce what the manufacturers do, et cetera. And of course, they're doing it to standards. The suppliers we choose also are fairly critical. We work with some companies that are developing materials, and so we have to be careful how we actually discuss what they do. Then there's other companies that have been around for a long time. This company has been around, I think, for over 120 years. And I believe there's some statistics, maybe not in this, but if you look at their website. But they're from Japan, and they do have a fairly substantial manufacturing capability. But more importantly, we know that they are suppliers to some very, very large names within the industry. And so it's nice to be able to work with companies that have extensive capabilities. But what they don't know is they don't have the applications understanding. So what we do is we look at our structures, because they're doing their testing to a standard, okay? And then we look at that and we can put that into our modeling. But that doesn't mean that when you develop a structure, which goes back to the question about electric fields and intensities and that, again, it's how do you make sure you're not exceeding at the highest point of field intensity, you're not exceeding what happens within your materials. And so this so we're looking at materials that we have a lot of confidence in to start with in most cases, working with manufacturers that have high reputations, have good reputations. But on the other side of the coin is we do our own testing to make sure that within the structures we're looking at from an applications point of view, we're still able to use their numbers as guidelines as design guides in what we do.
Okay.
That's it.
Great. Yeah. No, thank you for that. Next question. Can the spacer be placed on both sides for balanced heat flow?
Okay, so in terms of the thermal performance, so as Dr. Hopkins just introduced that, if you are placing the spacer underneath the die, you are increasing the copper thickness. But go to the certain thickness, you may not increase the spreading effect. So it will maybe just increase your thermal resistance instead. So you may not able to reduce entire thermal resistance. Yeah, so it depends. So you need to carefully design your button spacer's thickness. Yeah.
And let me jump in too, that we did a paper quite a while ago at APEC, and it's called Misconceptions of Thermal Spreading. And, you know, I'd given the scenario about the thickness of the copper, and it gets too thick, what good is it? And what people don't understand, the EEs don't understand particularly, and I hate to slam, I'm an EE, so I'm slamming ourselves, is that if you have a high thermally conductive material like copper sitting on a low thermal conductivity material, that's a lot different than looking at a scenario where you actually are reversing that condition. So the spreading, again, you know, putting a copper underneath the chip between the chip and the copper trace only adds thermal resistance. There's no benefit to it. Now, if your copper trace is not thick enough and you're not getting sufficient thermal spreading, well then a large thermal tab underneath for spreading is good. But I have another student right now, a master's student, that's revamping my course notes, because my course notes, I go through this whole thermal spreading problem. And basically, the example is a 5mm chip, and he's using 8 mils copper, which is more than, way too much. But anyways, 8 mil copper, but he only needs to extend the 8 mil copper out about 1 millimeter on each side of the 5mm chip, extend out 1 millimeter, and you're done. I mean, you spread about as much as you can spread. The asymptote, you've already hit the asymptote, and adding any more copper, spreading out any further, it doesn't do any good. And that's critical, because you want to have high density, you want your chips up close to each other, but how close can you put the chips? And if you put it underneath, and you want to put a fat spreader underneath, well, then you're basing separating out your chips more. So again, getting these design guidelines down helps in how to be able to lay out your patterns. Go ahead, I'm done.
Okay, thank you, Professor Hopkins. Next question. The person also said, by the way, nice job. So I want to pass that along to both of you, and I concur. But the question the person had is, what equipment is required to build laminated assembly? Can you provide a list of manufacturer model numbers?
Yes. Yeah, like I say, this is all open source. The pictures I showed at the very beginning, I think I give you the name of the company, and I give model numbers, but when you get on, we're going to have an open source, so you can you can duplicate my entire lab if you like. Sure, if you're interested in doing this laminate stuff, then just look at that first slide, and I'd be more than glad to send you everything except I'll black out the quotations of the dollar amounts, but I can send you the actual list of what we bought. I assume that answers the question.
I think so. Yeah, that's good, and appreciate that. What is the value of the HTC in the thermal simulation, and why do you choose the value?
Okay, so in the thermal cycling test, the high temperature stage, I select 150 degrees C because it is related to your packaging. Or for example, if you look carefully in the datasheet, there is a maximum operating temperature for this device or this package. So if the maximum temperature is 150, that means you need to pass the thermal cycling test at 150 as well, or you can do higher to make a certain buffer. So the temperature range depends on your maximum operating temperature of your device and package.
Okay, we do still have a few more questions, and a good number of you are still here, so we appreciate that. If we could back up to slide 22. I'll wait for that to back up, and then there we go. All right, on slide 22, what are the key factors driving the spacer thickness for isolation requirements?
Yeah, as I mentioned here, we can, for considering the mold flow when you are injecting your molding compound. And on the other hand, it is critical about the insulation distance. So it depends on your devices. So if you are 1.2 kV, there's a standard you need to follow. And also in different industry like automotive or aerospace, they have different standards. So it depends on what is your application area and also what is the voltage rating of your device. And that determines the spacer thickness in terms of the electrical consideration.
Okay, great, thank you. Next question is, how do you get the Pareto front?
Yeah, so it is the result in the optimization. So yeah, as I mentioned, both the sensitivity chart and Pareto front can be created by ANSYS. That is a powerful tool. So if you're really interested in how to do that, maybe you can send email to Dr. Hopkins and he can forward to me so I can show you how to go through those process. Yeah.
Okay, great, thanks. Thanks. We're going to go all the way back to slide 13 now, and so I believe that is in Dr. Hopkins' portion of the presentation. Yeah, since this question refers to the slide, can you please comment on the miniaturization of the module on the top right? And so I think that's the conventional IPM going to the new IPM.
Right. And so this is, I know this is not my work, this is theirs. And so I'm just reporting what they've done in the two references I've given. And Mitsubishi, this is, PowerX, they bought PowerX. And so this is all PowerX work. And that's all that I put them in there because I wanted to show the audience that from PowerX's point of view, this is the kind of reduction they've been looking at.
Okay. Next question we have is 5 kilovolts at 120 UM is at DC. How does this change with frequency?
We have not analyzed that yet.
Okay, that's a fair enough answer, and that's fine. Next question says, first of all, great talk from both. Very interesting application of flex hybrid electronics. Can you expand on the utilization of flex hybrid electronics in your work?
Okay, I guess I'll take this one then. So we see that, again, looking at what's going on in the microelectronics world, a lot of it, there's a couple of factors that get us into this. One is it has very high voltage withstand capability. And the other part of organics is the organics degrade. You can have graceful degradation of organics over time. It could well plotted out. And one of the things that's more sensitive to organics than you have with the ceramics is looking at what your life cycle usage is. And so that enters into it. You can have, again, higher reliabilities because of the modulus is so much lower. That's why aluminum is better than DBA is better than DBC. And so when you look at these, you're now looking at, okay, I can have higher reliabilities, but I am trading off in the fact that it's not going to be the same high thermal performance. but also the move to organics is you're moving to a much higher volume, lower cost platform for manufacturing. And particularly when you look in the GaN world, and you look at, and everything is going with silicon carbide, wide bandgap, and GaN's not doing it. GaN has taken us to very, very high frequencies. Silicon carbide has taken us to very high voltages. But of course, there's always that beautiful middle ground where you want to go to high voltage and high frequency. And so, so we see the organics as getting us to these very high volume, low cost systems where we can now start handling much higher frequencies. Because in the RF world, organics is typical. The RF world doesn't. They have their ceramics, but all of your all your telecom systems, they're working at gigahertz, are all in the organic world. So I think it's a big move for us to be able to start looking, not for us to start, we should have been doing it, for us to move into the organic world. I'm not sure if that answers it directly, but that's been the push that's my vision and why I've been pushing into the organics world now. It's the wide bandgap devices are just too fast, and they're just extremes in DVDT, DIDT, and voltages, and people want things denser and denser. And of course, it's always at lower cost and higher performance. That's it.
Okay, thanks. Next question, and we only have 2 questions left, so we're just about done. And again, appreciate everybody for attending and staying on through all this. A lot of great information here. Do you anticipate any adverse effect on the dielectrics from high speed and high frequency switching involving high voltage and currents, considering high DVDT and DIDT involved in such switching process?
Okay, so this is directly answered with partial discharge. Except if you're talking about the dielectric layer, this is strictly handled with partial discharge. As you know, the PD problem is, of course, we're always talking above the passion level. It's about 150 volts, give or take 20. So with the DVDT, and of course, you have to worry about what level, if you're going to go aerospace and what your atmospheric pressure is. But if you're talking about partial discharge, it's always, what is the purity of your materials? And that's why we have papers out there showing other packages that do very high voltage packaging for test. And by the way, I differentiate strongly packaging for test versus packaging for application. But anyways, when you package for test, we qualified a silicone. We're working with a vendor, Wacker. And Wacker, now we're working with Henkel, and with Wacker, they were developing their silicones, and you have to have a very high purity silicone for very high voltage. And if it's pure silicone, and it's in fact, we've worked with the 3M for a while, it's very critical. So not only is it contaminants, but also how do you make sure you don't have air bubbles? Part of the PD problem with dielectrics is you have these little air bubbles. The air bubbles represent little capacitances. Also, your voltage in that area is too high, and you're able to start ripping out electrons, and you start creating ions, which aren't cool, but they're locked into a solid form. But the other part is you start creating carbon. If you end up some of the material that's air is in there, you can carbonize. And so, anyways, you start creating these little conductive particles in these nanovoids. And so, all of that DVDT and DIDT. It's one thing to have the DVDT going from conductor through dielectric to conductor. Then the question is that capacitive discharge current that you're looking at through that conductor. That's the whole idea, right? It's a capacitor, right? And how much can you get through that? And so, so what are you doing to that dielectric as you start to be able to put such high stress, volts per micron or volts per nanometer, across the molecular structures within these dielectrics. It all gets back to what does your PD testing tell you about the purity and about the void rates, and then you can then extrapolate into what your DVDT across the dielectric can be limited to.
Okay. And final question. You mentioned PowerPower for modeling at the start of the presentation. where can one get a download of this software?
So ParaPower, yeah, so if you hop on our site and then go to ParaPower, the first introductory slide or tutorial tells you exactly where to go to the Army site to download this. Yeah, I mean, it's really cool. I mean, I think, EE is going to start, I could see it easily, EE is going to start jumping in on this. The problem with ParaPower is that it's written by I shouldn't say problem. It's the right way to do it. It's written by the heat transfer engineers. And so you can't fix a substrate temperature. And one of the biggest problems that we have in doing thermal analyses and what I review in papers on that is people, they assume a backside temperature and fix it as they do the analyses. You can do that in COMSOL ANSYS, et cetera. But that's not really what the situation is. I mentioned before how, you have thermal spreading depending on how thick your copper is, et cetera. When it gets to the back of the module, if you use a constant plate temperature across the whole back, you're not including any spreading effects. Whereas if you put a heat convection coefficient H on the backside, now you're getting much more of a true understanding of where the heat is going to be liberated on the backside of your module and how that reflects to your total thermal resistance. It's one thing to set the thermal resistance with a backside fixed temperature, but it's something else to actually say, okay, in the application, what can I expect out of this? And without that H factor, which EEs try to, typically don't include, you're not getting a really true understanding. So anyways, ParaPower is will be difficult for EEs because they're going to ask, well, what's the H factor in the back? So they'll have to run off and learn what H is, the convection coefficient is, and then how to be able to deal with it. And by the way, it's a value that can span anywhere from 500 to 2,000. So that's it.
Okay. All right, great. Thank you. And that does conclude our questions. So